Now, as you know, a solar cell, a solar panel, only generates optimal power if it's directed straight to the sun. And in the case of the ISS, since the station is revolving around the planet at 7.5 kilometers per second, you need to direct those panels actively towards the sun all the time. Now, of course, one option could be to keep the panels rigid with the rest of the station and to change the attitude of the station as it flies along its orbit. But this is really not a very good option because there are thermal considerations to be made. If there is a payload that is doing, for instance, Earth observation, then to have the station change its orientation with respect to the Earth would make the design of the Earth observation payload a lot more complicated, and also it would make the life of the antennas providing communication services to the ISS a lot more difficult. So this is not the option that was chosen by the designers of the ISS. They actually decided that each of the 8 solar array wings could be rotated along, or actually around, its longitudinal axis. And in addition to that, and more importantly, an entire group of 4 solar array wings could actually be rotated around the longitudinal axis of the integrated truss assembly. In this picture, you can see a close-up of both the rotary joint that ensures that the truss section can rotate around its longitudinal axis. This is called SARJ, or Solar Alpha Rotary Joint. And you can see the joint that makes sure that solar array wings can rotate around their longitudinal axis. And this is called the BGA, or Beta Gimbal Assembly. Now, there is one important difference between BGAs and SARJs. BGAs are used just to perform fine adjustments of the solar array wings orientation. They don't have to rotate all the time, and therefore they were not designed to rotate all the time. This is not the case for the solar alpha rotary joint. If we want the panels to always be pointed in the direction of the sun, we need to make sure that the truss makes a complete 360-degree revolution for every orbit. And that means that we need to have a joint that can transfer power and data across and not have the requirement of being reeled back at any point in time, which is quite the engineering challenge. And that's actually one of the reasons why the solar alpha rotary joints are such interesting fit of engineering. Now, if the solar arrays, if the solar panels are the most notable feature outside the ISS, then the second most notable feature are probably the thermal radiators. Now, this is a point that not everybody realizes, but once you have powered a piece of equipment, any piece of equipment, you really have a big problem in space to dissipate the heat that this piece of equipment is generating. And that's because in microgravity, one of the fundamental mechanisms that are used for heat dissipation on ground is not available. There is no natural convection, to say. And that's because in natural convection, when a part of air, when a quantity of air becomes hotter, it is lighter than the air that surrounds it, and because it's lighter, it moves up. And of course, the colder air tends to move down, thus generating what is known as a convective cell. Now, since there is no weight in microgravity, there is no lighter and heavier, so if a piece of equipment is powered on and nothing is done about heat, then the air that's around this piece of equipment, if it's inside, will just get hotter, and it will not be replaced by colder air. That means that the designers of the ISS, or the designers of any space vehicle for that matter, have to be very clever about the ways heat is being transferred from the point it is generated up to a part where it can be radiated to space. So in the specific case of the ISS, if I have a computer, for instance, active inside the station, and this is, for instance, one of the system computers, then this computer will be typically connected to a cold plate where water is circulated. The water takes the heat that is generated by this computer and transports it to interface heat exchangers where the water hands over, in a way, the heat to ammonia. And ammonia is the medium, is the fluid that makes up the external thermal control system, which is a large system of plumbing and piping that takes hot ammonia from the point where heat is collected to the thermal radiators. And you see here that there are actually two different types of radiators. Closer to the pressurized modules of the station, you have the main radiators, and those are used to dissipate heat that is generated almost anywhere on station except where the solar panels are located. For the areas where the solar panels are located, special radiators are being used. And to understand why you need different radiators for the solar panels, you need to remember and go back to the concept of the solar alpha rotary joint. Remember, this was a joint that has to rotate 360 degrees for every orbit, and that cannot be reeled back at any point in time. That means that it would be very difficult to transfer a fluid like ammonia across this interface. So to make things easier, there is one set of thermal radiators for most of the station, and then there is a different set of thermal radiators for the solar panels. This way, ammonia only has to be circulated in the area where the solar arrays are and in a separate loop in the rest of the station. You see in this picture a close-up of the main thermal radiators. Now, as the solar panels have to constantly point in the direction of the sun to have maximum power generation, likewise, thermal radiators always have to point in the opposite direction from the sun. They always have to point towards deep space so that they have maximum heat rejection. So, as the solar panels had rotary joints ensuring that they could move around the longitudinal axis of the truss and around the longitudinal axis of the solar array wings, likewise, thermal radiators have joints that allow them to rotate around their longitudinal axis. In this case, there is only one rotational degree of freedom. There is only one joint involved. And this is actually a very nice picture, not just because it shows very clearly the thermal radiators, and not just because it shows very clearly that thermal radiators actually can rotate, but it is also very interesting because it includes a number of very important elements that are located outside the ISS. One of those elements are the antennas. You see just in between thermal radiators, there is the station's Ku band antenna, very confusingly named space-to-ground antenna. And this is confusing because, at least in the early days, the space-to-ground channels, which are the voice loops that were used by the astronauts to talk to mission control, were going via S-band. So the Ku band antenna was not carrying the space-to-ground channels. And it is actually interesting to see why the Ku band antenna of the station is called space-to-ground antenna. Well, to understand that, we have to go back and see what was the nomenclature used in the TDRS for the antennas used to transmit and relay information from the satellites to either White Sands and Guam. And this was called, in that case, very fittingly, space-to-ground antenna. And the very same piece of equipment was used on the ISS. So it still was called space-to-ground antenna, even though in the early phases it was not carrying the voice loops. It was not carrying the space-to-ground channels. Now, also in this picture, even though not very clearly, you see some cones, which are actually the S-band antennas. In general, the ISS uses those two bands primarily. Ku band is for high-rate data, so for instance, video, while S-band is used for low-rate data, which is most of the telemetry, telecommands, and voice communication loops. Some other frequencies can be used on the ISS and are sometimes used. One of those frequencies is VHF, and you see one of the VHF antennas also in this picture. VHF is not normally used because VHF can only be used when the station is inside of a ground station. And as we have seen before, communicating directly to ground stations is not really convenient, and it does require quite the amount of resources. So S-band is only used typically in case of emergencies if the main station's communication system, which is the TDRS, is not working for any reason. Another element that is extremely important and that we will just cover in a second is the space station robotic arm, which you see in the picture here between the integrated truss assembly and the space shuttle. Now, the station robotic arm, or space station robotic manipulation system, is one of the most important pieces of equipment available on board. It is actually fundamental for ensuring that the station can be resupplied by cargo vehicles. You remember we have seen before that the station can be resupplied by Progress, but it can also be resupplied by Dragon, Cygnus, and HTV. Now, the Progress can dock autonomously or under astronauts' control to the Russian side of the space station. So, Dragon, Cygnus, and HTV cannot dock to the ISS. They can only get up to a point where the astronauts extend the robotic arm, capture the vehicles, and take them to the station so that they can be berthed to the US, to the American part of the space station. Which means that if on a very bad day we lost the use of the robotic arm, we wouldn't be able to use 3/4 of the cargo vehicles currently available for the transfer of both pressurized and unpressurized cargo. Now, if that weren't enough, the robotic arm is also used to transfer the unpressurized cargo from the vehicles all the way to the place where they need to be located, all the way to their permanent home. And you see in this picture a very nice shot of the robotic arm taking one unpressurized payload from the trunk of the HTV and moving it away. This was actually one payload that had to be located outside the Japanese module, and the choreography of the operation was extremely interesting because the payload was carried in the trunk in the unpressurized cargo bay of the HTV. The HTV was berthed to the ISS, then the station robotic arm was taking this payload out of the trunk and handing it off to the Japanese robotic arm that would complete the installation outside the ISS. And of course, as we've seen before in the section about solar panels. The robotic arm is a fundamental element in EVA operations. A repair, like the one performed in 2007 on the solar panels, would not be possible if we didn't have a robotic arm available.